In this physics problem, we're looking at a spring system on the Earth. So the problem is, on Earth, a mass of 0.05 kilograms is attached to a vertically hanging spring with a spring stiffness of 14.81 newtons per meter and a relaxed length of 0.2 meters. You grab the hanging mass and hold it so that the spring's length is 0.25 meters. Then you release it from rest. So, what it's asking in this problem, it wants to know what the net force of the mass is just after you release it. So we have some constants over here. This is our mass right here. This is our spring constant. This is our relaxed length. This is our length once we pull it. And then this is what we're looking for. This is our F net. So first off, we have to know what makes up the F net of the entire system. So now we have gravity, and we also have the weight of the spring itself. So let's go ahead and draw a picture right here. We're going to draw it. So this is the ceiling. So this is our spring. And then this is the spring at 0.2 meters. This is the relaxed length. This equals our LO. And then this is it once it's stretched out the entire way. This is our 0.25 meters. And this is our length once it's been stretched. So we know for this that we have two factors working on it. What are those factors? It is the F net of our spring equals the force of the spring, because the spring is pulling it up. And then we have gravity, because it's just going straight down in the y direction, and that's the gravity of Earth. So we know first we can solve for our F of Earth, and that would be just the mass of the spring, so 0.05 kilograms, times gravitational constant of 9.8 meters per second squared, because we are on Earth. So that would equal 0.49 newtons. But because it's going in the down direction, we know that it's going to be negative. So the F Earth of that system is 0, because our x direction is not moving, negative 0.49, because our y direction is moving, and then 0 in the z direction, and that's newtons. So we know our spring system is our other force acting on this, and we know the formula for a spring system is negative Ks times S times L hat. So pretty much you can look at the S and our L hat, and that is pretty much the change in your length. So that would be 0.25 meters minus 0.2 meters, because that's our relaxed length, is 0.05 meters. So that's how much it changed. So that is our S and our L. And then we got our spring constant, and that's a 14.81 newtons per meter. And then we know that that's negative because there's a negative sign in front of it. And then because the spring is being pulled down, there's also a negative sign in front of our change in the spring system. So then our meters cancel, and we're left with just 0.7405 newtons. And again, this is just moving in the y direction, so you need to technically write this, because this is our spring force. Spring. This is our spring force as well. So technically you need to write this. The x direction is 0, the y direction is 0.7405, and the z direction is 0 as well. So that is our F spring and our F Earth. We know that all that's left is to add the two together, because that's F net from back up here. So F net equals our spring, so that would be 0, 0.7405, and 0 newtons. So that is our spring constant, or our spring right there. And then the Earth is 0, negative 0.49, and 0. And that would be newtons as well. So you add the two together, and your new F net is 0 in the x direction. Make sure x direction is not moving this entire problem. 0.2505 in the y direction, because you add those two numbers together, and then 0 in the z direction is in newtons. So this is your F net of your spring system right here.